Hi, I'm Lukas, a fourth-year PhD student at ETH Zurich.
And I'm Nicolas, a first-year PhD student also at ETH Zurich. In this talk, we present Zeph, a platform that enables cryptographic enforcement of end-to-end data privacy. This is joint work with Alexander, Hossein, and Anwar. 2.5 million terabytes was the estimated generated data per day in 2020. And the pace at which we create and generate data is growing exponentially. What is important to highlight here is that much of this generated data is personal and hence inherently privacy sensitive. For the most part, this rich data has enabled tremendous innovations in various fields, ranging from health, agriculture, and industrial automation. However, this did not materialize without issues. The accumulation of sensitive data has made service providers hosting data lakes a desirable target for attacks. In addition, a surge of incidents of unauthorized data monetization and sharing has raised serious concerns. This has pushed regulatory bodies to enact data privacy regulations to prevent data misuse. If we look at the landscape of data privacy today, privacy frameworks remain shaped by regulatory requirements that predominantly focus on the notion of notice and consent. Even though these are an essential step towards transparency and user control, it is important to emphasize that user consent is not the answer to data privacy. Bad practices in data use and sharing remain pervasive in consent-based systems. In recent years, we have seen breakthroughs in the design of effective privacy-enhancing technologies. For example, consider differential privacy, which is a prominent example in this space. However, solutions in this space remain ad hoc efforts for highly customized applications rather than a more general end-to-end approach that integrates well with existing data ecosystems. This is mainly because our data systems have evolved in a world where privacy was not really taken into consideration. So naturally, the question arises if we can do better.
In this work, we introduce Zeph, a privacy platform for streaming data which follows a system design that naturally fits into the structure of existing stream processing pipelines. Zeph addresses the issues of the current status quo of data privacy with two key ideas. First, Zeph follows a user-centric model for privacy. This means that users can set their privacy preferences and service provider must adhere to them if they wish to use their users' data. Second, Zeph cryptographically enforces privacy, meaning data is encrypted at the source and the service provider can only access the data in form of a privacy-compliant view. Or in other words, the data can only be decrypted in a form that complies with the user-defined privacy policy. To understand how Zeph works, let's look at one application scenario. Here we consider a service provider that serves a fitness application like Strava, which allows logging fitness activities such as cycling and running with a wearable device. In this application, the service is, among other things, interested in providing an overview of the most popular running tracks in a city. This is an example of a service that requires combining data from multiple users to provide a useful utility to its overall users. To achieve this, a privacy transformation that is derived from users' privacy policies converts raw location data from different users into a privacy-compliant view of the data. In this example, a privacy-compliant view can be realized by masking certain areas and generalizing over time and users. In the current status quo, we typically have a privacy policy, which is a legal text document that could describe that such a privacy transformation is applied. However, there is no automatic enforcement or any kind of guarantees and assurances that the data processing and handling comply with the claimed privacy policies. Here in this work, we are interested in ensuring users are guaranteed that the data is transformed with the privacy transformation corresponding to their privacy preference. Meanwhile, the original data remains end-to-end encrypted. So essentially, we want to enable privacy controls for end-to-end encrypted systems. Privacy transformation are tools to confine what can be inferred from the underlying raw data and safely release data. They achieve either a range of privacy guarantees common in practice, as in aggregate statistics, or formal privacy definitions, such as k-anonymity or differential privacy. There exists a broad set of practical tools to realize privacy transformations, such as data masking and data generalization techniques. In Zeph, the goal is to support a wide range of these tools within an end-to-end encrypted setting. So let's look at the current status quo of end-to-end encrypted data in streaming pipelines. We have a data producer that encrypts data locally and sends it to the server for encrypted storage and processing. Users can later then query or retrieve their encrypted data and decrypt it locally, for example, to check their activities and track their progress. However, in end-to-end encrypted settings, it is not directly possible to provide a service such as a heat map because the encryption leads to per-user data silos that cannot be computed across. Within this setting, there are three core issues that arise in a compelling approach to end-to-end privacy. First, The first core issue is that an approach to end-to-end privacy must be compatible with existing systems, which means that we want to leave the flow of end-to-end encrypted data untouched. The second core issue is that in a user-centric model for privacy, users can have different privacy preferences. This can result in data that is associated with heterogeneous sets of privacy policies. The challenge is then to organize data and use it to extract value in a way that adheres to the user's different privacy policies. The third core issue arises because we want to keep data end-to-end encrypted. Hence, we need to find a way to allow privacy transformations that can be computed on encrypted data across multiple trust domains and only reveal the privacy-compliant output of the data. One solution to this problem can be realized by integrating privacy controls into the data producer. So basically, give the data producer a privacy policy and make the data producer responsible for enforcement of this privacy policy. To enforce the policy, a data producer would, in addition to sending in data encrypted to the cloud for storage and processing, now also participate in a privacy protocol to facilitate the transformation. Examples for such privacy-preserving protocols that can be executed without trusting the service could be Rapport or Pravio. While these are good practical protocols, they are ad hoc solutions that do not integrate well into existing data pipelines and complicate the logic at the data producers, which are often resource-constrained edge devices. Zeph follows a different approach to end-to-end privacy and proposes a new design. A key idea of Zeph is to leave the existing data plane intact and to add a separate independent privacy plane on top of it. In the privacy plane, we introduce a new component called the privacy controller, which is responsible for enforcing user-defined privacy preferences. A key benefit of decoupling the privacy plane from the data plane is that the privacy controller does not need access to the data to authorize transformations, and that the data producer is unaware of any privacy controls. Privacy transformations are executed in the untrusted service and consume encrypted data from the data plane. Zeph introduces the concept of cryptographic privacy transformation tokens. These are tokens generated by the privacy controller to authorize transformations. In essence, these transformation tokens are the required keying material that is needed to obtain the output of a privacy transformation. For transformation involving data from different users, we require interaction between the different privacy controllers in what we refer to as federated privacy control. In Zeph's threat model, we assume a fully trusted client side, which involves both the data producer and the privacy controller. And we assume an honest but curious adversary on the server side. For the federated privacy control, we assume a limit on the fraction of parties colluding with the server. Now we look in more details on how Zeph augments existing streaming pipelines. Zeph introduces a proxy module, which encodes and encrypts data streams at the data producer, privacy controllers that authorize transformations with transformation tokens, new jobs in the streaming pipeline that execute privacy transformations, and a policy manager component that collects the privacy preferences from users and orchestrates privacy transformations. Now we address the challenges that arise when going from a user-defined privacy policies to a platform for end-to-end privacy.
The first challenge is that we need to find a balance between being expressive and keeping the end-user control simple. Streaming pipelines support different types of data, and what types of privacy transformations are sensible depends on the underlying data and the involved data utility. In Zeph, we augment existing streaming schemas with policy options that outline the set of possible transformations. To keep the end-user control simple, in Zeph, we envision a system where users can set simple privacy preferences that are valid across different applications. For each application, there is an application-specific policy choice, which is a mapping between the available policy options and the high-level privacy preferences. This mapping can be defined by experts and is available for auditing. The second challenge is around organizing privacy transformations. On the one side, we have different policy choices from different data streams. On the other side, we have different streaming queries expressed in Zeph's query language. The job of the policy manager is to find a privacy-compatible matching between the selected policy choices and the streaming queries to organize privacy transformations. After discussing two of the system challenges, now we move more on the crypto side to see what challenges arise there and how we address them in Zeph. First, we need an encryption scheme that provides confidentiality of data. Then we require that the privacy controller can authorize transformations. So transformation can only be completed with the proper transformation token. The privacy transformation must be able to be computed on top of confidential data. So we require a form of a homomorphic encryption scheme. And lastly, the privacy controller must be efficient and independent of the data. A concept that is closely related to the defined requirements is homomorphic secret sharing, more specifically additive homomorphic secret sharing. And for this, we take a closer look at Zeph's privacy transformations. In homomorphic secret sharing, the data producer splits the data in two shares and sends one share to one party and the other share to the other party. In Zeph, this corresponds to sending one share to the service in the cloud and one share to the privacy controller. Note for additive homomorphic secret sharing, the additive shares can also be seen as a ciphertext and a key. This can be repeated for multiple pieces of data. The main insight is that the privacy controller manipulates the keying material to create a token, while the privacy transformation applies the same transformation on top of the encrypted data. In the end, the token can be combined with the transformed encrypted data, which decrypts the privacy transformation. Confidentiality is guaranteed since the encryption scheme is CPA secure. The privacy controller authorizes the transformation by sending the token. Now for the third requirement, is this additive homomorphic scheme sufficient to support the privacy transformation that we target in this work? In the paper, we show that indeed we can use client-side encodings to support a wide range of the existing privacy tools with only addition. Check the paper for more details. For now, to give you a general idea how privacy transformations are supported in Zeph, I'll walk you through an example. In this example, we consider a privacy transformation that first hides sensitive parts of the data, aggregates the remaining data across users, and then adds noise to achieve differential privacy. Here we have an event consisting of two fields represented by the two shades of orange, and both are masked. We can imagine that the first field is something that we are willing to reveal under certain conditions, and the second field is personally identifiable information that we don't want to reveal at all. For the example, we have a second data producer that produces data according to the same schema. Both data producers send their keys to the privacy controller and their encrypted data to the cloud. For now, we are going to focus on how the privacy controller can manipulate the keys to enforce this transformation. The privacy controller first redacts part of the key, then aggregates the keys from different sources, and finally adds the carefully calibrated noise. The outcome of the transformation is a transformation token that authorizes these privacy transformations. Now let's look at the service provider side. The only thing that the service provider can do is apply the same aggregation on the data. Afterwards, the service provider can decrypt the noisy view of the data by combining the aggregated ciphertexts with the token from the privacy controller. Note that the other privacy transformations in Zeph work in a similar fashion. Okay, so this demonstrates that privacy transformations can be executed on top of encrypted data. However, in this model with additive homomorphic secret sharing, the privacy controller is yet not independent of the data producer and also not efficient because aggregating the keys is basically the same work as aggregating the ciphertext. We address these two problems with two ideas from our previous work in TimeCrypt. We can make the privacy controller independent of the data producer by using a timestamp encoded key derivation function. And we can make the privacy controller more efficient by using a key canceling technique. So far, we've looked at the case where we have multiple sources of data, but only a single privacy controller that creates token to authorize transformations. However, in most scenarios, it's not possible to only have a single privacy controller because no single entity is trusted by all users. So it's necessary to split the trust into multiple privacy controllers that are responsible for enforcing the privacy of different data producers. For this case, Zeph includes a secure aggregation protocol, which allows the three privacy controllers to safely construct a token of aggregated keys without revealing individual keys. In the paper, we show how to optimize an existing secure aggregation protocol specifically for Zeph.
To evaluate Zeph, we implement a full prototype of Zeph design. The prototype implementation of Zeph augments Apache Kafka and Kafka streams. We implement the data producer in Java and the privacy controller with Java and Rust. In the paper, we provide an evaluation of Zeph to assess its overhead compared to a plain text system in various settings, and implement 3 applications on top of Zeph. In this talk, I present the evaluation results of the web analytics application, which collects user statistics of a website that consists of multiple pages and serves a privacy-compliant view of these statistics. For the end-to-end evaluation, we distribute the data producers and privacy controllers across 3 AWS data centers in Europe, while the data processing runs in Frankfurt. Here we have the end-to-end latency of Zeph to execute the complete privacy transformation in the web application, compared to executing it on plain text. We benchmark transformations involving 300 or 1,200 data producers with the same number of matching privacy controllers. Zeph incurs a sub-second overhead for 1,200 participants compared to the system in plain text that does not provide any security or privacy guarantees. We consider this overhead to be modest compared to the additional privacy guarantees Zeph provides. We observe similar numbers for the other 2 applications. Thank you for your attention. For more information, please check our paper. You can find the Zeph artifact on our GitHub repository, which allows to easily experiment with Zeph. Thanks again.